All right, so wavelets. So wavelets for us is kind of the pinnacle of what you can do using classic transform techniques, okay? And so basically, wavelet is what is being used in JPEG 2000, and JPEG 2000 is the best-in-class, off-the-shelf, lossy compression format you can find, okay? So you probably haven't seen that too much yourself, but say if you go to see a movie, okay, so the movie in the theater is packaged, it's compressed for the reasons I've explained in the introductory lecture, which is like there's way too much information. You cannot store possibly hundreds of terabytes of data like that. So so it's compressed, and it's compressed frame by frame using a JPEG 2000 format, and JPEG 2000 format is wavelet, basically. Right? So that's it. I think it's used in medical imaging as well, and it's kind of the de facto standard for archiving. Okay, so you might not see that too much as a consumer. You see what you see is JPEG, but JPEG 2000 is very much used by companies and so on to archive their data and so on. All right, so wavelets. So there's different ways of looking at wavelets, and the way we're going to look at it in this particular course is through the angle of filter banks, and from the angle from what I've seen. So the wavelets, they had a lot of theory built by a number of Belgian mathematicians in the 90s, I believe, 1990s. And if you look at the Wikipedia page on wavelets, you have a totally different view from what I'm going to show to you here, okay? So the angle you're going to have from wavelets here is different much from a filter bank point of view and from Z-transform and so on, okay? So the good news for you, there will be much less mathematical theory to discover, and it's just more kind of how to look at wavelets, to have an introduction to wavelets as an extension of what you've already seen. Okay, so let's look at where we start. Okay, so we started from a transform. Okay, so we looked. So remember from the DCT course, from the handouts on DCT, we started to say, okay, so the hard transform is a two-point transform. So we had 2 points, and we had this matrix transformation. And I transformed that back into 2 points. And we looked at the DCT and say, well, actually, you can have a multiple point transform, 8-point transform, and so on. And what we're going to look at here is like to say, well, that can be viewed as some filter operations as well. So when you do the transform, okay, you see that. So maybe I'll flip to here for a second. Okay, so remember when we looked at, we had a stream of, so we're looking at the 1D case, of course, okay? So 1D signal. So we have a stream of values. And the first thing we do is we take a pair, we split that signal into blocks, and then we say, well, you multiply this block by a transform. So that's just a matrix multiplication on that. And what you get is an output, and you just write down the result of that output for that particular block, okay? And you do the same for the rest, okay? Now, when you look back at what the transform was, so that was your transform for the 1D case, and we look back at the exact equation that what it gave us, then what we observe is that it kind of looks like a filter, okay? So here we're doing a low pass, we're averaging two consecutive values, and here we're taking the difference, okay? So now obviously this is not a filter because we only apply that on 2 points only, and we don't apply that continuously. But what if we did, okay? So we could define two filters, and we're going to say that the so this is what you do, okay? So in this is what we're going to do here, okay? So we are going to define two filters, so y0 and y1, and basically they are going to implement, if you want, your half transform, but in a continuous way. So instead of chunking that into blocks, you say that this filter, we compute the low pass version, the low pass band of your half transform, but instead of doing that block by block, it's actually going to ingest a continuous stream of your data. Okay, so you say y0. So y0 is the result of that particular filter 0, and is the average of the current point and the previous points. Okay, so that's what you do. And then you say that this guy, so the second filter, is the difference between the previous value and the current value. All right. You can write that as FR filters. So you have H0 and H1, and what you get is H0 is, all right, so this is where we have to be careful. So we're looking at the previous sample, so that's Z minus 1, and so you have Z minus 1 plus 1, and Z minus 1 minus 1 here. Okay, so this will be the two filters you apply, okay? Now, obviously, when you do that, then it's not quite right, okay? Because you cannot produce too much information, okay? So, so let's come back to that. So in a way, what we're saying here is that, okay, so y1 is this, and that's the results of this filter taken at value 2, okay? And here we say this is the results of this other filter taken at value 2. But when you move on to this next pair, you're going to see you're going to have a gap, okay? Then you have to say, well, this is the results of y0 at value 4 and the result of y1 at value 4. Okay, so you're kind of missing, you just not actually, you don't need the results of y0 at 1 or y0 at 3. Okay, so you only need the results of these values at every second, every odd or every even sample. Does it make sense? Okay, so you have these two filters, and they kind of helper functions to compute that, if you want. But then you realize, like in practice, to actually do the transform, you have to throw away half of the information that the filter will give you, because you actually never need the result of that filters at 3. Okay, you just don't use that. Okay. All right, that's what I explained here. Okay, so this is how we get it. You see this kind of skip. You need the results at n, but then you just need that n plus 2, and you don't need that n plus 1. And that, in terms of just pure filtering operations, or the kind of stuff you have in systems, that corresponds to downsampling. All right. So this is the kind of the heart of the building block of what's to come. Okay. So you have on the left your signal xn, so that's a digital version, and the z transform will be x of z. That comes into these two filters, so H0 and H1. So remember, H0 is kind of this average, so low pass filter, and H1 is this high high pass filter. So you get the a filtered version, but what you do here is you throw away half of the information because actually you don't need the values that are defined in between. Okay? And so effectively what you do is you downsample your signal by 2. Okay? Does it make sense? What's going on here? All that makes sense, okay? Here we have one signal, okay? When you do the hard transform, the signal doesn't change in length, okay? You don't get more stuff, okay? So the number of samples you have is the same. But what we've done here is to say we have a signal, we apply one filter, one convolution, so we get one result, and we apply a second one. So now we have 2 versions of your signals, okay? So you have twice as many samples that you set it with. So you need to downsample by half to get back to just the correct size. All right? So that's the first step, okay? So then you have the reconstruction, okay? So we know how to encode, to do that version, to get the hard transform level 1. And now we need to be able to decode it. And basically, it's a very similar operation, but because we know it's just the inverse, right? So we can do the same, and the argument goes as follows. So you say, right? So you know from the pair from the equation. So these are the equations you need to have. This is just the equation as you have as the inverse transform. Okay, but the way we had downsample operation here, what we need here is that would be called an upsampling operation, right? And so we are going to take upsampling operation. So right. When you have something like that, so just let's look back at the fundamentals of that. Okay. So if you have a signal xn, and if you have an operation like this, that means if you had x1, x2, x3, x4, after a downsampling operation, what you'll get is x1, x3, x5, x7, and so on. Okay? So you remove every single sample. If you do the upsampling operation, so starting again from the same signal, so x1, x3, x5, x7, that's your input signal. If you upsample, what you do is you insert zeros. Okay? So you recreate a signal of the same length as the signal you started from, except now you replace every single sample by 0. Okay, so you insert zeros. So it's quite important here. Okay, there are different ways you could do upsampling. Okay, you could try to interpolate or do put in between values or replicate the values and so on. But here, when we introduce that particular symbol up by 2, that means actually I insert 0. Okay, so the value I insert in between my points is 0. Okay, so it's quite important. All right, so let's look back at what we have. Okay, if we define these 2 filters, okay, so if the same way we had before, so we had this is kind of the input of the reconstruction, and this is the values we have that is only defined every second pixel, and this is a transform to get back to the pair of values we need. Then we could say, well, we could define that as being a continuous filters by saying that if you define so xn as being the result of this addition of 2 filters, and these 2 filters are defined for values of n plus 1 and n, and I'll let you do the work of the math for that, but basically you have 2 cases. Either n is even or even is odd, and depending on which one is which, you either be this configuration here or this configuration, and you get back on your feet because if you have, say, 2n plus 1, then you have an odd value, but because we upsampled, we define that as being 0, so that cancels out. Anyway, it's just something you need to come back and carefully look at. But basically, the reconstruction goes as follows. You say that the reconstructed filter is the summation of these two filters that are defined as the inverse of your Haar transform. And this is the final system. So on the left, you have what's called the analysis. So that's your forward, this is your Haar transform, okay? So what you get from that is the subsampled version of the two bands. Okay, so that's your low pass and your high pass. And this is the version where you upsample those, apply these two filters, and here we just combine them with a plus. Okay, we just add them, and you get the reconstruction. All right, so you have a slight asymmetry in the treatment, and into here you have a split, and here you have the way you join both signals just by doing an addition. Okay, so both these versions are exactly the same as the operations done in the Haar transform. Okay, all right. So another way of looking at it is, like you looked at that in the 2D domain, but there's this kind of two views. Like either you looked at the subbands themselves, or you looked at the interleaved transform. Okay, so if you apply the transform as just you split into blocks, apply the metrics, then you kind of have, when you look at your stream, at the transform, you have the interleave low and high, low and high, low and high, low and high every second pixel. Okay, and we've seen with the 2D Haar transform, it makes sense to reorganize all that into these little rectangles and the quadrants that you have, sub-images, so you can actually see something that looks like a picture. And in a way, that's what you do here. You say, well, I'm only looking here at the low pass of the signal, and I'm going to gather all that into a sub block, okay? And so that's what you get here from Y0. Okay, so Y0 is your, the equivalent for you in the 2D Haar would be the low sub-image, right? So that's half the resolution, like you subsample your picture. And when you do the inverse, what you do is you have to upsample that picture, apply this filter, and just add the stuff, okay? All right? So what we're going to do now is to look at that from the point of view of the Z transform. Just checking the time here. So now that we have everything kind of, expressed neatly as filters, and you have these operations of downsampling and upsampling, then we can work in the frequency domain and see what's going on. Okay, and this is what we'll do here. So the nasty part, of course, is this downsampling upsampling operation that we haven't looked into much details. Okay, so I leave that for you to read in the slides, but basically this going down and up again has the same effect of doing that in the Z transform domain. Okay, so what you do here is say, I started with Y0 of Z, and at the end of that process here, I have a signal which is half of Y0 of Z and plus Y0 of minus Z. And basically, what is happening here is this is exactly what you get from, if you remember the part of the handouts on subsampling and aliasing, all right? So remember when you subsample signal, what you get is you get multiple versions of a replication of your spectrum, and they overlap, okay? And what you do as well is you rescale that and so on. So basically, if you just look at that from the from the Fourier transform point of view, when you apply the downsampling operation, you're going to create replication of your signal, and you're going to reduce as well the scale. And when you upsample the signal, then you're going to reshift things back and so on. And this is exactly what's happening here. Okay, y0 of minus z is basically in the Fourier. So remember, z is like your omega, the frequency that you have. So it's exponential of j minus omega. And basically what you get here is a replicate. This guy here is your aliasing. Okay, this guy here corresponds really to the replication of your spectrum that adds to your original signal. Okay, so say that again. This is kind of like, this is your original spectrum, and this is the aliased version, like the replication of your spectrum that will be added and that will cause all the aliasing issues. All right. Here's all the derivations of why you come to that. There's a bit of maths involved. It's not hard at all. But this is what I wanted to say. Okay. The Z transform relationship between the Fourier transform and the Z transform is basically you say Z is exponential of j omega. All right. And because when you look back at the equation, it's exactly the same. So when you have that here, if you replace Z by exponential of j omega, you realize that minus exponential of j omega is the same really as exponential of j omega plus pi. All right? Because exponential of j pi is minus 1. All right? So taking minus z is the equivalent of taking, if you want, the Fourier transform and shifting it by pi. Okay? And for us, because the Fourier transform will be replicated every 2 pi, now we have this extra replication at pi, and that's exactly what is happening when you do your downsampling. Okay? So there's no surprise when you do the maths that you downsample at some point your picture, you're going to have this aliasing effect happening. Okay? And I just wanted to point out that when you see a minus z, that minus z is a replication of your spectrum. Okay? Probably have lost all of you here, but read back in there, okay? And just remember that when you identify, when you see these guys, you'll be like, oh yeah, this is what's happening in aliasing. This is this additional mirror of your spectrum being replicated. So I just wanted to finish with that, and why do you go through the process of doing that? Okay, we do through the process of understanding the Fourier domain is because we want to say, well, the same way we kind of looked at the DCT and say, question the fact, why do we use the Haar transform in the first place? There's maybe other optimal transforms. Okay, and here the same way we say, well, we have defined 2 filters. H and the reconstructing filter pairs as well. So you have H0, G0, and you have H1 and G1 in your graph. So coming back here, you see you have 4 filters defined. Okay, and the question is, what can we do? I mean, either we know from the Haar transform that when you have start with X, you encode and decode, you get back on your feet. But the question will be now, can we define any kind of filter H0, H1, G0, G1? What kind of pairs of, or are there any constraints, any conditions on these filters that will make it not work or work? Okay, and these conditions are called the perfect reconstruction, and that's something we're going to see tomorrow. Okay, so indeed you can define a whole range of filters. Like there's a relationship between these filters so that it all works fine. You can come back on your feet. But they need to meet the perfect reconstruction criteria that we'll see tomorrow. All right, that's it.